All right. Well, thank you so much for having me at this conference. It's been great. I was going to say it's been great so far, but it's actually coming to an end, unfortunately. So, but we have Slack, so we can keep this going. Uh, so as many others, most of you probably, when singlet state NMR came around, when it was invented or revived, or whichever way you want to look at it, it was just so incredibly amazing to see these long lifetimes. And I'm pretty sure, everybody was asking themselves, well, how long can they be? What's the maximum? And and uh, and I think the Levitt lab and Giuseppe Pileo's lab probably hold the world record. This is in a paper from a couple of years back, and we've heard from Mohammed that he has measured even much longer times than that. So this is pretty amazing, and this gives me a good opportunity, by the way, to say in this field, actually in many areas of NMR. The lab of Malcolm Levitt and Giuseppe Pileo and others, that's kind of like abrogam. If you think you have a nice idea and then you find out, oh, they actually published it a couple of years ago. So so that's good and bad, I guess. So so here are the questions that specifically are of interest always when looking at these questions. So can we use singlets for polarization storage? Of course, as a contrast agent, maybe for measuring like really slow processes. What limits singlet lifetimes? Which relaxation mechanisms are those? Can we design molecules with particularly long lifetimes? Now, the questions, they're probably kind of just different ways of asking the same thing. And I think more recently, another question developed based on just having more understanding about all these things is, can we study new relaxation mechanisms and not just study them? Can we maybe also use them for structural or dynamics investigations? And so how do you measure singlet lifetime? So first of all, I hope you can see my cursor here. So so you have the storage period here where you store the singlet state, or, Christian Banks reminded me this morning, we should call it singlet order. And sometimes we need a spin lock for that. Sometimes we can just leave it there without a spin lock, depending on what the system looks like. Now, to get it there, we need to write the information. We need to write the polarization or the labeled magnetization in a certain way. And that can be done either with parahydrogen. It could also be done with DNP, or with an inequivalence, like chemical inequivalence or magnetic inequivalence, in combination with pulse sequences or field cycling. You might say, field cycling is just another kind of pulse sequence. So then we need this writing mechanism. So we need some kind of inequivalence. And you could say, well, if we use a reaction with parahydrogen, there is some kind of inequivalence that was introduced at some point there. So then we store it, we wait for some time, and then we have to read it out. And again, there we need inequivalence to be able to read it, because the singlet state itself is indetectable. And what we have pursued, and others, is to use a chemical reaction as readout in combination with pulse sequences. So so if you want to lengthen singlet lifetimes, there are of course a couple of simple things you can do. Remove neighboring spins. So deuterate the molecule if you can, deuterate the solvent if you can. So get rid of other spins. Now, of course, again, the Levitt Lab and Christian Banks and Stuart Elliott have shown if you have deuterium, you might also run into some other unexpected problems like scalar relaxation of the second kind. But fortunately, that one actually can be decoupled. So either way, so removing spins is a good approach. If what you're shooting for is just the longest lifetime, or you want to know what is the lifetime limiting mechanism. You can also increase symmetry. And again, the Levitt Lab published this work where they've shown if you have an inversion center in this molecule, they've shown it in particular for a carbon-13 singlet, you can lengthen the lifetime very significantly. And this is due to the fact that the chemical shift anisotropy mechanism is effectively turned off by having this symmetry. Interestingly enough, they also published another paper saying high symmetry doesn't guarantee a long lifetime, and both is true. So you have to proceed carefully with how you interpret these things. So what we have pursued was we really wanted to work with very symmetric molecules and to increase the symmetry in what we have, and use as the right mechanism, use the pyrohydrogen, and as the read mechanism, another chemical reaction. And we had this series of molecules, which basically, I mean, a lot of people studied these. So Kirsten Miniman was talking about this, the malleate and the fumarate derivatives. And this one would have the inversion center. And we mainly studied the proton singlet. And it's probably true that this molecule, for some reason, it has just these nice qualities. It's an organic molecule. You can dissolve it in organic solvent. So it's kind of, these properties sort of evolutionarily designed it probably for us to use it for these studies. And then in this work, so we had, we put the pyrohydrogen here, and this is Yuning Zhang and Peiqi Sun who was doing the work with the injection device. So then we inject a solution to convert the malleate to the fumarate derivative, and because we wanted this inversion center here. And what we got was a kind of anticlimactic, and so 5.8 minutes. It wasn't significantly longer than what we wanted. The sad conclusion was this is not infinity. We, at that point we were sort of hoping we would just get a huge long lifetime with all this effort. And in analyzing this, though, it became very clear that what we have is a lifetime limited by oxygen. Even though we're trying very hard to get rid of oxygen, it's just very hard to do it in regular NMR tubes. But it's also very hard to do it if you're injecting, two different solutions and you have a reaction. So you're gonna have some amount of oxygen in there, and just a small amount will affect the results. And around the same time, Boris Karkov in my lab also discovered that if you're measuring very long lifetimes, you might have a problem with convection, thermal convection. So you might even have a case where the spins diffuse out of the detection volume during that time because of thermal convection currents. And this would be the velocity profile across the NMR tube, the cross section. And then you might see something like this. You might see oscillations even due to that. And so he developed a couple of strategies, including that we should always confine the sample within the detectable volume. That's a big factor. Spinning helps, spinning the sample helps. And also what he then used was what I call the obsessive compulsive experiment. So he used M to S and S to M here for the triplet to singlet conversion and the back conversion. And each of the 180-degree pulses he replaced by a composite pulse, but not just a 3-pulse composite pulse, a 25-pulse composite pulse. So that's why I call it obsessive compulsive. But it really works. It made the difference. It makes a difference between 300 seconds, measuring 300 seconds, and 580 seconds. So that was really, really important. So these findings that we have oxygen and we might have convection made us move away from these fairly complicated experiments where we wanted the highest symmetry, because we realized, yes, we want the high symmetry, but we're going to have these problems with oxygen and potentially convection. So then we wanted to do more controlled experiments, and then we moved to this molecule, ethyl propyl malleate. And again, this is one that Pileo and John Nicolas Dumas have studied already, both the carbon and the proton singlets. And we used the malleate because what we found is that for protons, this actually has the longer singlet lifetime, longer than the trans version, even though the trans version has the inversion symmetry. So it has a longer lifetime for the protons. And what I'm showing here is the magnetic field dependence. So we didn't have access to a lot of different magnetic fields, but at least we got a couple. And then this point is from the red circle is from Giuseppe Pileo's experiment. And if we just fit a polynomial of order 2, this is what we get. And then we have this huge unaccounted for contribution. So what is this? What mechanism is this? Now it's easy to say, well, most likely we have some oxygen in there. There is perhaps some residual dipolar contribution, but how much? You know, what is the limit? Is there something we can get rid of? And the same we found in sort of field cycling experiments where we used this fishing line setup. Boris built this to move the sample to specified magnetic fields during the waiting period. And we could simulate everything, including singlet triplet leakage and CSA relaxation over a big field range, except for this constant offset. So we still didn't know at the time what it was. So so then it became clear we really have to move to molecular dynamic simulations to get more insights into that and to explore what is the level of the potential strength of the relaxation mechanisms that we can have. And there is a lot of work on molecular dynamics in NMR and for NMR relaxation, but I believe this paper by Perry Hawkinson is probably the only one that specifically was done to study singlet lifetimes. And this is a really great and deep paper. And he did the work while he was in the Levitt lab also. And I was hoping that we could learn from that approach, or even better, I was hoping we could ask Pierre to run the calculation for us. And unfortunately, that never materialized. So so we realized we had to basically acquire the know-how ourselves to figure that out. So then we started running these simulations using, for example, in this case, Amber. Here are just some parameters to give you an idea of what the size is, the size of the calculation, using a 50 angstrom box. The compound is dissolved in chloroform. And we take 100 samples from an NPT ensemble and then propagate each for about a nanosecond unconstrained with NV. So then one of the nicest things you could do from molecular dynamic simulations is to calculate the contribution of the dipolar coupling relaxation mechanism. And that's another, at least, for us, it was another hurdle to take because it's the equations are there. By the way, also published by Giuseppe Pileo in a, I believe, JCP paper. So the equations are there, but it's kind of a bit of a zoo with these equations. It takes a while to make sure you find all your factors of 2 and all your factors of pi and all your factors of 10. So that is occasionally, that can be an effort. And so, but also because of this problem, we thought it would be a really good idea to have sort of a benchmark that we could use, where we could test whatever we calculate on. And it turns out we had, in our sample, we had an internal standard. We have chloroform as a solvent and deuterated chloroform. And we also measured the R1 of chloroform over the temperature range, where we also measured the singlet lifetimes for the compound that we're interested in. And chloroform relaxation has been studied a long time ago, and it's quite well understood. So you have spin rotation as contribution. You have dipolar coupling between the proton and the chlorine nuclei in chloroform. So even though we don't normally talk much about chlorine, it has a spin, and there is this pretty sizable contribution to relaxation from that. And then, so you have the intramolecular, and then you have the intermolecular between proton and deuterium, and proton and the chlorines on the other chloroform molecules. It's interesting, by the way, for chloroform that the intermolecular relaxation for chloroform is stronger than the intramolecular one. So, so we ran then this these MD trajectories. So what we have in there is the compound. So that's the ethyl propyl malleate. Then we have one oxygen in the box, one oxygen molecule, and then we have the chloroform solvent. And then we extract the relaxation rates using all these elaborate formulas. So for chloroform, we then were able to calculate spin rotation based on ab initio spin rotation tensors. Then the intermolecular proton chlorine dipolar coupling, the intermolecular interactions, and the remaining portion must be from oxygen. So how do we calculate oxygen? We calculate oxygen as a dipolar relaxation mechanism between the protons on the chloroform and the electrons on the oxygen, and those are considered spin 1. And we also use a T1E, an oxygen T1E of 15 picoseconds. I can say a little more if needed about how we chose that. So we have to add all of these up. So just to guide you a little bit here. So this line here that increases, that's the spin rotation mechanism. It increases at higher temperature as expected for spin rotation. Then we have this one is the sum of all the dipolar regular dipolar contributions, and then this one is the oxygen contribution to chloroform T1 relaxation. And now there is a free parameter that we have because we don't know how much oxygen we have in the sample. We try to remove it, but we don't know how much there is left. And so this adjustable parameter, because we know there are no other mechanisms for chloroform, we can figure out how much oxygen is there in the sample. Because as far as I know, there isn't any other good way to figure out how much oxygen you have in the sample. So we get this good match here if we add all of these up, and then we apply all that knowledge to the compound of interest, where then we can calculate the intramolecular proton deuterium interaction, the intermolecular proton chlorine interaction, proton deuterium interaction. These are all broken out here, down here. These are all the dipolar interactions, and you see there is the intramolecular is just as strong as the intermolecular. So this is a really interesting finding because in the end, you're going to dissolve your compound in some solvent, and you'll be hard pressed to find a solvent that doesn't have any spin. Like, of course, we try to get rid of protons, try to remove them, exchange them for deuterium, but deuterium is gonna have some contribution, and even chlorine is going to have some contribution. So well, maybe CO2 as a solvent would be a good choice. So so that's one thing. And then for oxygen, we take what we find for oxygen for chloroform T1, we take that information and plug it in here and get the contribution of oxygen. And if we sum all of these up, we get this line here. And this is the experimental line. You see there is still some disagreement here, and this job is not completely finished. I believe we could get agreement here from considering the CSA contribution. So we know there is some fairly weak CSA contribution, and the temperature trend goes in the right direction. So I believe it should be possible to get good agreement here. So I want to move on to a slightly different system. So a while ago we got very interested in a collaboration with UCSB, with Matthew Fisher and others, including Song-Hee Han, who is part of this consortium, to study potential quantum effects in the brain. And I don't want to oversell this idea. Let me acknowledge right away it's a pretty crazy idea, and I would myself probably find 10 reasons to refute it. but it's crazy enough that it's interesting, and it's and I encourage you to read about it. This article by Matthew Fisher. One of the things that is true is phosphorus is one of the most isolated nuclei in the body in terms of at least dipole interaction. And so the idea was born that maybe phosphate long-lived spin states can store information, and then they can get entangled, and then they can transmit information over far distances. Again, I don't want to be too attached to this idea. For me, this was good enough as a starting point to look at phosphates and to look at phosphate singlets. So what we wanted to study was pyrophosphates, for example. But you already see the problem here. It's you cannot make a singlet, or at least not. It's not too obvious how to make it. There is not enough inequivalence. Well, there is no inequivalence here if unless you consider doing something with oxygen 17, which is probably quite non-trivial. And so how do you make the singlet, and how would you then read it out? So so we have, and by the way, one collaborator of Malcolm's, Linda Brown, synthesized the compound with oxygen 18 that we started measuring. But there are also other questions that are hard to resolve about proton or deuterium exchange, which there was some talk early in this conference about oxalate, I believe, and squarate, where a similar effect is seen. So we wanted to leave these questions aside to have a little more control over the question first, to understand what is happening, so and then come back to this. So the first compound that somehow came to us, or that we thought would be a better starting point for looking at this, was this one, tetrabenzyl pyrophosphate. It's a magnetically inequivalent system. And what I also, I mean, what is kind of really nice are the spectra, because you have this compound and it looks symmetric, and then you take a spectrum and you get a whole mess. And it's because of this magnetic inequivalence, and it all actually makes sense. It doesn't make sense in the sense like, like a textbook thing. You talk about AX2 and that kind of thing, and we know exactly what the spectra look like. Not like that, but you can simulate them. And these simulations were done with spinach, by the way, and thank God for spinach. I should say it really saved us a number of times. And also the proton spectra of the methylanes are really, really interesting here as well. So or at least I have not seen a spectrum like this before, and it all can be rationalized by magnetic inequivalence. Actually, there is a slight chemical inequivalence for these methylanes too, because of the spherical hindrance. So anyway, so these parameters are all figured out, and this work was done by David Koranchan and Jiaqi Liu, and they optimized the singlet generation parameters and use this zero rank filter here, again something by Giuseppe Pileo and Levitt, Malcolm Levitt, and then measured the singlet relaxation, and the result was disappointing. It was disappointing. So RS was 3 times R1. So basically, the TS is much shorter than the T1. And why? And so we started looking into the CSA mechanism, and for me, the starting assumption was always, well, if we have the symmetry, it looks like maybe we do have I mean, this is maybe not a good chemistry intuition statement, but it looks like, well, maybe we have something of the equivalent of an inversion center. Then maybe these interactions should really go away, like described in this paper. But it turns out when we run the molecular dynamics that this is not the case, and I'm sure a lot of proper chemists know the answer. You don't have the inversion symmetry at all, and you have this angle between in the phosphate in the bridging oxygen in the phosphate bridge there. And from here, we then extract molecular dynamic snapshots, calculate CSA tensors, and these are beautifully displayed here with spin dynamicas function. I believe this is in the pre-release version, the function ovaloid, that can very beautifully display these tensors. And what we see here is very clearly that these tensors are never aligned. They are about 60 degrees off of each other all the time. And that is the source of this anti-correlation of the CSA tensors, which leads to this enhancement of relaxation. So with these calculations then from molecular dynamics and these ab initio tensor calculations, we can match, in fact, the T1 and the TS pretty well. I think is a pretty good agreement here over the temperature range studied. And also what's interesting here is that the antisymmetric contribution of the tensor is very small, is as opposed to the example in the Levy group paper, where they had actually a big contribution of the antisymmetric portion. In this particular case, it's the symmetric contribution that is the major contribution. So, I'm coming towards the end. I just want to say one word about phosphates, one more thing, and this is part of this quantum brain collaboration, where we've also found there is also a strangeness in relaxation unrelated to singlets. We have found surprising behavior of T2 relaxation with temperature. And we have also found in CEST experiment evidence for a dark state population. Dark meaning you don't observe them directly, but you can observe them indirectly. So I believe for phosphates, at least, there is also an additional side to this story that may also affect singlet lifetimes. So to conclude, well, so if your goal is to have the longest lifetimes, I think most people know this, to remove coupling partners, increase symmetry, but within reason. Symmetry doesn't always guarantee that for you. And of course, the Levitt group have additional recommendations, such as constrain the molecule, reduce internal motions. But this is a big one, oxygen, and I think most of you know about this. It's a big one and it's a hard one, and it's definitely, if you have irreproducibility, most likely it's because of oxygen, and it could be also convection. So, and molecular dynamics helps identifying mechanisms, such as we can now calculate, well, what is actually the contribution of oxygen? What is the contribution of dipole coupling to chlorine nuclei, for example, which normally we don't think about. And then what's interesting is the symmetric and antisymmetric CSA contributions. And I would advocate, if you can, to use an internal standard, such as the solvent somehow. In this particular case, chloroform happened to have a very long T1. For water as a solvent, water wouldn't be such a good choice, but in the chloroform was a good one. So I want to thank a lot of people, in particular David Karanchan, Jachi Liu, and Boris Kharkov, and then the collaborators at UCSB on the quantum brain work. And I was very fortunate to have Diamond Jubilee visiting fellowship at the University of Southampton, and still have, because of the pandemic, it was extended. And I want to thank Malcolm for his hospitality, and all the wonderful people from his lab, Mohammed, Christian, and Jyrki, who I've had wonderful conversations with. So thank you all for listening.
Thank you so much, Alexej. That was really inspiring and gives some really good guidance for how to measure the long-lived singlet states and the considerations of CSA. One quick question about CSA. Obviously one way of removing CSA is just to go to very low magnetic fields. Have you kind of tried that a couple of times in some of these molecules?
Yeah, so we did one study, not in the phosphates where we really had that very strong effect. We did it in the other kind of the malleate derivative with this field cycling with the fishing rod thing. And so yeah, so I mean, obviously that is, if you can do it, that's actually the best way. That's a great way for you to just avoid open, you know, you don't have to speculate. Is it CSA? Is it something else? Here you have it, right? You can see it. It's very easy to simulate. In the case of the phosphate, in the context of the quantum brain, well, I have to say, you know, one thought I had was, well, if at high field you have such a short singlet state, does that mean that your magnetic field can affect cognition?
Right, right.
You know, and again, I don't want to end at this crazy note, but it was just a thought.
Yeah. No, I'm very fascinated. I'm very fascinated by those thoughts, actually. I think there's a famous Nature paper from 20 years back or so that postulated a quantum computer with phosphorus, hyperpolarized phosphorus. But of course, it was never realized. It was just like a theoretical prediction. But anyways, I guess, you know, not only cognition, but maybe also quantum computing with phosphorus spins isn't entirely crazy and out of the question. So, you know, if you can initialize a pure state in a system like this, maybe through hyperpolarization, such as with parahydrogen, then this could be possible. And the system, especially this molecule that you're studying currently, strikes me like it might actually happily bind to Saber complexes. So you might actually hyperpolarize singlet states inside of the phosphorus spins like that. So we can have a chat about that if you like. Okay.
Yeah, that sounds
Hey, Alexej, great talk. I wanted to have a follow-up question on the quantum brain idea. I admit I'm not really a believer in it, but it occurs to me that if that were something that were to happen, I guess I would assume that nature would select for molecules that have unusually long-lived states. And correspondingly, if you don't find any examples where that's happening, right, where you don't see that selection, then might that be evidence against it?
Yeah, no, it's absolutely true. So the way I approach this topic is, and I kind of said it during my talk. So I use this as a motivation. I use it as a motivation to study phosphate singlets, to see what are the mechanisms. I'm not using it as a starting point to say, well, yes, so now we have found evidence for or against. And it's easier to find evidence against, for sure. And we already have evidence against. But I nonetheless, I encourage you to read that paper by Matthew Fisher. It's actually quite, I mean, the way he writes is not yeah, is inspiring, I think.
Oh, thank you.
Yeah.